Hello everyone and welcome to our universe. Today we'll be talking about the lifetime of a star. When we look up at the night sky, the stars never really seem to change. In fact, throughout your lifetime, the stars may never change whatsoever. Night after night, century after century, so many people have assumed through history that they have lasted forever. The Greek philosopher Aristotle even proposed that stars were made of special elements, not found on Earth. Since Aristotle's time, astronomers had discovered that stars, like people, have finite lifetimes. Stars are born from great reservoirs of cosmic material, and these are the most common elements in the universe. They shine with immense brightness and give off so much energy for millions if not billions of years. However, stars do exhaust their energy supply and eventually die down and go extinct. Understanding the lifetime of a star has been one of the greatest tasks in astronomy, at least during the last 100 years. Astronomers have made remarkable progress in tracking the progression of the stages of a star's phase. So let's review the broad outlines of a star's story, and how an astronomical object can be discussed in a sort of lifetime, from birth to death, and understanding every stage that a star usually goes through. So a star begins their life in a kind of incubation, when a dense region happens to form from a huge cloud of dust and gas. The material that will make up the star falls inwards under the influence of gravity. As the clump of star stuff gets more and more compressed, it heats up, first with infrared energy, and then through visible light. As gravity continues to pull the infant star together, the center of the collapsing ball of gas gets hotter and hotter, until temperatures at the middle reach an astonishing 10 billion degrees Celsius. At this temperature, protons can collide so forcefully that nuclear fusion can occur. Physicists call this reaction fusion because protons that originally formed in the nucleus fuse together to make the nuclei of heavier atoms. In a star like our Sun, 4 atoms of hydrogen eventually combine via fusion to make a heavier nucleus of helium. What makes fusion inside of a star so useful is the transformation of the element, making it into a slightly heavier one, and this releases energy. The combined energy released by billions and billions of individual fusion reactions flows outward from the star's core. Some of it eventually emerges from the star's surface as light. The pressure of sunlight, along with particles blown off the surface of the newborn star, sweep away from the surrounding cloud of gas and dust, and therefore a star is now born. Most stars are born in groups. These are often called star clusters. Clusters like this that stay together allow us to track the stories of the stars, while less massive clusters will simply dissolve because of the lack of gravity. These stars in less massive clusters will eventually mix into the general population of the Milky Way. Most stars will simply wander the galaxy until they get into a stable orbit, very similar to how a planet orbits a star. The outward push from nuclear fusion in its core is now nicely balanced with the inward push of gravity, and the star remains in this balanced state for about 90% of its lifetime. This is now at the stage that the Sun is now in. It's been at this stage for almost 5 billion years, and it will continue to do this for at least another 5 billion years more. Having a stable star is thought to be critical to the development and evolution of life. How long a star lives depends on how much material or mass it has. Massive stars have a lot of gravity, which makes the centers extremely hot, and therefore they tear through their hydrogen atoms extremely fast, and exhaust their fuel very quickly. The most massive known stars last only a few million years. The core of the lower mass stars, like our Sun, is a lot less hot, and burns its fuel a lot more slowly. This means that our star can last for billions of years, rather than just millions. The lowest mass stars, known as the dwarf stars, burn very, very slowly, and they may last more than 100 billion years. This is much longer than even the current age of our universe. Nevertheless, the core of every star eventually runs low on nuclear fuel. At this point, the star experiences a bit of a crisis. Gravity is still compressing the star, but the outward push of fusion begins to suffer. A complex series of events then occurs, which leads the star to collapse on the inside whilst it swells up on the outside. As the outer layers of the star grow larger, they cool off and become reddish in colour. A red star is cooler at its surface than a white star. Astronomers call these type of stars red giants, and they can become as large as the orbit of Mars or even Jupiter. A particularly dramatic example of a red giant is the star Betelgeuse. It is 425 light years away from Earth in the constellation of Orion, so it's astronomically quite close. It has now grown to be 600 times larger than our Sun, and were it to replace our Sun at the centre of the Solar System, it would completely swallow the orbit of all of the inner planets. But all red giants eventually do find a new source of fuel, but the star is never quite the same again. Some of its outer layers are permanently lost, and its resumed inner stability is only temporary. The lifetime of stars splits into two branches. The low mass stars, which is our Sun, have only a limited ability to squeeze their cores to continue the fusion processes. They experience a period of instability, where their outer layers lift off. This period of instability for those stars produce some of the most beautiful objects in the night sky. As a star shreds its outer layers, the gas inside of it is illuminated by the light of the collapsing star, and glows in an array of colours. These are the last gasps of a dying star. These objects were named planetary nebulae because they resemble disks of planets, although we now understand that they have no connection at all to planets, but the name of course has stuck. So on the other hand, high mass stars have significant pressure and temperature at their cores, and this means that they can continue the fusing process by using these newer, heavier atoms that they formed earlier. Helium, carbon and oxygen are each in turn becoming fuel to make more energy for the star, and this is fighting against the gravity. And this keeps the star stable, at least for a brief time. Eventually, however, the massive star's core becomes composed of simply iron, which sets off the final collapse and the catastrophe. When low mass stars die, they collapse under their own weight, until their centres act in the same ways like a solid. A star like our Sun will collapse at the end of about twice the size of Earth. These white-hot dying stars are called white dwarfs by astronomers. Perhaps the best known white dwarf orbits the brightest star in the sky, Sirius, but it requires quite a large telescope to see it. Massive stars are very different in their ending. When the core of a massive star collapses, its powerful gravity takes it right through the white dwarf stage to produce one of two extremely bizarre objects, either a neutron star or a black hole. In most cases, the rest of the star blows up in a gargantuan explosion called a supernova. These explosions produce so much energy that the star can briefly become brighter than the entire galaxy in which it's located. This is approximately brighter than 100 billion suns. Extreme versions of supernova explosions are sometimes referred to as hypernovae, and these produce gamma-ray bursts. The most famous supernova in history was in July 1054. Records of this still survive, from China all the way to North America. Seen today, roughly 1,000 years later, its remnant is called the Crab Nebula, and it is one of the most interesting objects in the night sky. It can be found with a good pair of binoculars or a small telescope in the constellation of Taurus. Near enough every star leaves a corpse star corpses come in three bizarre varieties. A white dwarf fades away as billions of years pass, since no energy is being produced inside of it, and light is escaping off into space. The star's corpse slowly cools down and becomes black as space. Astronomers call these corpses black dwarfs. A supernova explosion leaves behind a far more compressed corpse. The violent end to a massive star produces so much pressure that the star's core experiences a remarkable subatomic change. Electrons, that are negatively charged particles which orbit the nucleus of the atom, are actually squeezed into the nucleus. The electrons join with the protons to become neutrons. The process also removes all the space within the atom, leading to a fantastic compression of a star's remnant. To make something as dense as a neutron star on Earth, we would have to take all the people in the world and squeeze them into the size of a raindrop. But I wouldn't really recommend that. If the dying star is especially massive, the remnant becomes a completely collapsed object, known as a black hole. In these objects, gravity is so strong that nothing, not even light, can escape. Space, time, matter, and energy are all trapped within a tiny region. Understanding the behaviour of black holes is one of the great frontiers in the area of astronomy. So, by looking at a life story of a star, you might be thinking to yourself, how does this interact with human life here on Earth? What's the difference between life and death and previous generations of stars when it doesn't have anything to really do with humanity? The thing is, stars have a chemical makeup, and it all started when the universe began, with only the two simplest types of atoms, hydrogen and helium. It is not possible to make something as complex as a human being out of just these two elements. You need more stuff. So you need things like carbon, oxygen, calcium, iron, and a host of other atoms to make a human being, or life in general. So where did these heavier elements come from, if they were not present at the start of the universe? Well, heavier atoms had been produced by nuclear fusion, at the centre of stars. We see much evidence that stars create new elements in the process of making energy. When stars die, and especially the ones that go supernova, they seem to recycle their material, blowing these newly made elements into the cosmos. The next generations of stars then forms from these enriched mixtures of elements, and therefore so do planets. It took several generations of stars to enrich our neighbourhood, so that when the Sun and the Earth were formed 5 billion years ago, they would contain enough of the heavier atoms to make living creatures. Every atom inside of the human body, apart from hydrogen and helium of course, was once part of the inside of a massive star, and from this process it can create new life, not only for new stars, not only for new planets, but living, organic creatures. So I hope that's given you a great insight into the lifetime of a star. If you want to know any more about stars, or how they evolve and how they die, or maybe even how they've created life on the planet, I'll put some links in the description below. And as always, if you've enjoyed the video, click the like button, and if you want to support the channel, click subscribe and support our Patreon page. Thank you for watching, and thank you for your support.